All right, in this video we want to talk about systems of equations, solutions of systems of equations, and even maybe how you find uh, solutions to such systems. So, systems of linear equations. First, follow the definition. What is a system of linear equations? Well, it's simply a finite set of linear equations. So, it's possible that we can deal with infinite sets as well, but for the purpose of this class, we really only want to look at just finite sets of linear equations. So if I say I have a system of equations, you know I don't have infinitely many equations. I have only a finitely many of them, right? So a finite set of linear equations is what we would call a system. Now, a solution to a system, so a solution of a system, is to put this in a parallel to what we call a solution to an equation. A solution to a system is a sequence of values boy, can you read that? A sequence. I'm going to have to get a better pen here. I believe it's coming in the mail. So a sequence of values that when you assign those values to the variables, they make all the equations in the system true. Right? It's a sequence of values that when assigned to the variables, makes the equations true. Make all equations true. I'm going to be very curious to see how my new pen does. This is just a bigger tip. I got one coming that supposedly is much more accurate, but we'll see. If it improves my penmanship, that'll be great. Let me show you an example here. If you had something like 3x plus y equals 5 and 4x minus 2y equals 0. This is a system. It has two equations. It has two variables in it, x and y. I'm choosing to use different letters rather than the subscripts. We do both, but here's an example. So this is a system. I notice that if I let x equal 1 and y equal 2, that I think makes both equations true, right? Because if I plug a 1 in for x, so I've got 3 times 1 plus 2, that is 5, and 4 times 1 minus 2 times 2 is 0. So yeah, there is a solution. There is a set of values, 1 and 2, that when I assign them to the variables x and y, I make both equations true. This is a solution to that system. Okay. Now, systems come in all shapes and sizes. Actually, they come in one shape, but different sizes. They come in essentially rectangles. So here's what I mean by they come in rectangles. I'm going to write down my first equation here. It's a1 x1. I've got to leave space. I'm going to leave a little space there. I'm going to leave a little gap. So this is a1 x1, and then I'm going to add on to it plus a2, and I'm leaving a little gap there, x2 plus dot dot dot, and the last one would be a little gap here, n xn equals b. Now, this is my first equation, and I'm going to have another equation and maybe another equation. So what I'm going to do is I'm going to use what's called a double subscript on these coefficients. So this is going to be a11 x1, a12 x2, a13 x3, a1 and xn, and then I'll call this b1 on the end. So that's all the first equation, and I've got these subscripts of 1 something, 1 1, 1 2, 1 3, so on. So the next equation is going to be a12 x1 plus a22 x2 plus, and so on, all the way up to a2n xn equals b2. Okay, so notice the variables are the same, x1, x2, all the way up to xn, so it's the same variables all the way. The coefficients are different. The a11 is different than a12, so that those could be two different numbers. The subscripts are essentially telling us where we are. The first subscript is telling us which equation. The second subscript is associated with what variable. So when I talk about a76, that's going to be the seventh equation, the coefficient in front of the sixth variable, and so on. Okay, so you have, you know, a couple of equations, maybe you have more, so dot 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 down to, let's say we have I want this, let me go down, let's say we have m equations, so this would be a m1 x1 plus a m2 x2 plus all the way down to a m n xn equals bm. So my last equation might be the mth one, and I don't know what m is necessarily, but it's some finite number, and it's just got coefficients am1, am2, am3, and so on, all the way up to, I should be a plus sign right here, dot 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 plus amn xn, and then this is the bm. Okay, so this would be sort of your general system of, it doesn't make much difference, about the same size here and there, isn't it? Actually, I can make it all look bigger by closing this. Close that and zooming in. So that's my system. It has n variables of m equations, so they look very rectangular. In fact, we often would associate a matrix with this. Now, a matrix is just a rectangular array of numbers, and we will do a lot of things with matrices. This is just the first thing. And we make a matrix which is called the augmented matrix for this system, and essentially we just write down the coefficients and the constants over here. So the first row of the matrix is going to be a11, a12, all the way up to a1n, and then I have b1 right there. And then the next row would be a21, a22, all the way up to a2n, and then that's b2, and then all the way down to the very last one, which would be a m1, a m2, that's an m, all the way up to a mn, and then bm. So this is what's called the augmented matrix for this system. We will work with matrices in lots of different ways, as I said, but this is just the first thing. It just sets it up, sort of makes it a little easier to write, keeps things organized, and you'll see we have nice ways of using the matrix to help find solutions to the system. Now, I should point out that if the b's are all equal to 0, I'm going to come over here and say if b1 equals b2 equals all the way up to bm, if all of those b's are all equal to 0, we say the system is a homogeneous system. Homogeneous system. Each of the equations is a homogeneous equation. It's a linear equation where the constant is 0, and you've got a whole system of those things, and then you have a homogeneous system. Okay. Now, as we've seen, systems have solutions sometimes. There's also times when systems don't have solutions. And so we have a couple of different words that I want to put out here. So let's get this box back here. Slide that down, slide this up. All right. We say a system is consistent if it has at least one solution. If it has at least one solution. Consistent. It is inconsistent if it doesn't have a solution, right? Inconsistent if there are no solutions. And I just want to finish this video by pointing out that we represent solutions rather than writing it all out, x1 equals, x2 equals, whatever. We will often just put the numbers in a set of parentheses with commas in between. So 1, 2, for instance, looking back up at the equation that I had here, this equation had this solution. That solution I can write as an ordered pair 1, 2, where it's assumed that I know that this value is being plugged into the first variable and this is being plugged into the second variable. Likewise, if we had 3 variables, we might have an ordered triple. 4, 7, 9 would mean that x1 is equal to 4, x2 is equal to 7, x3 is equal to 9. This is not unfamiliar to you, I hope. Let's rephrase that. This is familiar to you, I hope, and that this is the way we, describe coordinates in the xy plane or in the xyz space. But where this is an ordered pair or an ordered triple, we might have something that's got all kinds of numbers in it. 3, comma, -2, comma, 7, comma, 0, comma, 4.9, comma, pi. So this has 1, 2, 3, 4, 5, 6 different values in it. It's an ordered 6-tuple. In general, we have what are called n-tuples. So they look just like this, a bunch of numbers arranged in a row with parentheses on the outside and commas in between the numbers. And if there's n of those numbers, they call it an n-tuple. Right? Just a way that we have, from the point of view, are we talking, if this is a point on the plane and this is a point in space, is this a point in 6-dimensional space? Yes. Yes, it is.